So we have been talking about equivalence principle, and for equivalence principle to hold, there is a requirement, and the requirement is that local space-time should be flat. What does that mean? Which means that, let's say you consider the Earth's surface, and if you have two balls which you drop, you know that if this distance between the balls, let's say d, is very much less than r, you can assume Earth to be flat, and that's what it means, that the local space-time is flat for this particular experiment. I do not have a quantitative definition of what really local means, but according to Professor Bernard Schutz in his book, the local depends on that how local is your experiment, depends on strength of the non-uniformity of the gravitational field, non-uniformity of the gravitational field, and the other thing is that how sensitive experiment is to non-uniformity. Makes sense. For example, here this is let's say r is, we know that r is around 6400 kilometers. So I don't know if d is of the order of say 1 meter, you can with confidence say, okay, this is, I mean, for d equals 1 meter, this experiment, for this experiment we can assume flat space to be flat, um, which means it has no curvature. Okay, now what are the various implications of this? First of all, g mu nu tends to eta mu nu. I'm using eta mu nu right now, but actually eta mu nu means minus 1, 0, 0, 0. Let's not worry about this right now. Let's just write g mu nu tends to flat space time metric for local inertial frame. Moreover, the first derivative of g mu nu is 0 in the local frame. Why is 0? Is 0 for the same reason why the first derivative of a potential is 0 at the bottom. Here we know that this holds true. For the same reason, for similar reason, this also holds true for metric. Also, we know Christoffel symbols are nothing but depends on the derivative of g mu nu's. So Christoffel symbols vanish in local frame. Well, you have to choose certain kind of coordinates called normal coordinates, because we know we can always make a transformation such that in flat space we can always make Christoffel symbols 0 by transferring it to an appropriate frame. So if choosing normal coordinates, in the local frame, Christoffel symbols vanish. Same for g mu nu. Now you see the first derivative is 0, but the second derivative of metric is not 0, is not equal to 0, because that is what um, gives curvature, which means later we'll learn about something called Riemann tensor. Riemann tensor is sort of a function of the second derivative of metric. Um, and Riemann tensor is something that encodes the information about curvature. As an example for this guy, I can give you an example. For example, the gravitational bending of light. We know that if there is a star and this light ray that is being shot, is going to bend, the gravitational field is going to bend it. Now if you just use, so you see you can there's some deflection from initial to final. This was the original path, and it gets bent to give you a different kind of path. This new alpha is given as 2gm over c square r. Gm is the mass of the star, and r is the distance between the star center and the light ray. Okay, this is from Newtonian mechanics, Newtonian prediction, but according to GR, we know it's a factor of 2, so this is 4 gm over c square r. Now if you have the experiment in which you have Earth and you have this light ray which you shoot, then it's going to bend down because of gravity, and if we consider the local experiment, then this deflection alpha, which will be, is going to be something, this local deflection alpha, I'm just going to exaggerate it so that you can see it's not going to deflect so much. This alpha, it will be proportional, or sort of will depend on the term y over r, which is nothing but coming from Newtonian mechanics, where y, by y I mean the distance from here to some point where you're calculating a deflection. R is nothing but the radius of the Earth, plus the second order term, now which will be actually y square, actually y cube over r cube. So this is Newtonian. The first order in G is, the first derivative in G is 0, so there's no y square or r square, but this comes from curvature. Now there may be some other terms. I'm just giving you a simplistic picture. It's not really an exact expression. Just giving you a simplistic picture that there is a y over r dependence because of Newtonian, and the y cube over r cube dependence which comes from curvature. Now if you really integrate it from the beginning to the end, this guy is going to give you 2gm over c square r, and this guy is going to give you another 2gm over c square r. So this is just mostly hand waving. I'm not really giving you anything quantitative, just to give you an idea. The curvature is actually a second order effect in space. We'll talk more in the